as well. So what they're trying to get you to do is they're trying to get you to understand how I'm going to work through my dimensional analysis. So we're given an equation that's going to provide length, and we're given some constant c for that length, or some constant c in our equation that's for the length, and we're told that this is in terms of time squared. So what we want to know is c is some number with the appropriate units to get the equation to work. So we're trying to find the units of c. So we're given x is equal to some number times time squared. My units of x are in length. My units of time are in seconds squared. So I'm going to have to divide both sides by seconds squared. So in order for this to actually provide length, my units for c have got to be length divided by seconds squared. And that gives me my units. So what they're trying to do here is a way to give yourself a check for when we're working problems, which we're going to be doing a lot of today. We're going to be working a lot of problems today, to show that I have clearly got my equations correct. So here's another one. We were given this equation. This equation happens to be Newton's law of gravitation. And we've got some big G, which is a fundamental constant of the universe. And we want to find the units of G in order to make this work. Now, we haven't quite gotten there, but we have talked about fundamental units and derived units. So a fundamental unit would be like length, would be like time, seconds, mass, kilograms. When we get to physics 2, charge is a fundamental unit. Lumens for light is a fundamental unit. But for what we're doing, our fundamental units are going to be length, time, and mass. So length is going to be in meters, time is in seconds, mass is in kilograms. But we can derive a whole lot of other units based on those fundamental units. Those fundamental units of kilograms, meters, and seconds. Well, force, if I'm in the English system, is going to be pounds. If I'm in the metric system, it's a Newton. And 1 Newton is defined as a kilogram meter per second squared. So we've got that kilogram meters per second squared. So what we'll have when we look at our other variables that we have in the equation, we have mass is going to be in kilograms, radius is going to be in length, that's going to be in meters, and the units of G is what we're trying to find. So I'm going to plug in units for each of my variables. I'm plugging in kilograms, meters per second squared for my force. I have mass 1, kilograms, mass 2, kilograms. R is in meters, and that gives me meters squared. So now I'm going to take this over here, and I'm going to multiply by the inverse on this side. So I've got my kilograms squared, my meters squared. So now this is my newtons, kilograms, meters per second squared. And now I'm going to end up in these weird units of meters cubed, seconds squared, kilograms. And we want to verify that that's correct. So what I'm going to do is I'm going to plug that in for G. And if I got my meters cubed divided by meters squared, that leaves me with 1 set of meters. I get rid of one of my kilograms because they cancel out. And now I'm left with kilograms meters per second squared. And I've got kilograms meters per second squared. And I verified that my units are making sense. So the whole reason that we're doing this, again, is to give us to make sure that we're working the problem and getting the right values. So let's do a problem that's going to help us look at this as well. So we've gotten through chapter 1 enough that we now have our 3 equations of motion. And they are, my change in x is going to equal my initial velocity times time plus 1/2 acceleration times time squared. I've got velocity final is equal to velocity initial plus my acceleration times time. And I have velocity final squared is equal to velocity initial squared plus 2 times acceleration times the change in the x. So right now, all I'm going to do is look at this in terms of our units. So what we're going to do is we're going to take, we have a car at a stop sign. And after we start up, the car is going to travel a distance of 200 meters in, we're going to do it 30 seconds. So that's the information that we're given. We've got a car at a stop sign. Once it starts, it's going to travel a distance of 200 meters in 30 seconds. We can be asked a lot of different questions. One question we can ask is, what is the total distance traveled? We can be asked, what is the acceleration? We can be asked, what is the final velocity? We can ask, what is the time required to reach 100 meters? Now it's physics, so there's usually more than one way to solve the problem. But we also want to look at this problem and kind of step through it and watch our units to verify that our units are going to help us out. So usually what happens when we start with a physics problem is the first thing you want to do is draw a picture. And that kind of reminds me that it is helpful for folks. You can print out your WebAssign homework. I would recommend doing that. Because what couple of things, if you print out your WebAssign homework, you can work on it as we go through problems like this. The other thing is that you have documentation that you have done your homework, and if there is a computer glitch, you can always take a picture of your homework and show me that yes, you did it, and you can submit in that written problem. Because I know I have a lot of athletes that travel, and sometimes the internet's not kind to us. Sometimes you will run into that you think you're entering a value into WebAssign, but you have lost connection with the server. There's all kinds of things that are there. So I do recommend that you go ahead and print off your homework, and that way you can have a paper copy of that homework. It's also going to be helpful for many of you, as many of you are going to be taking the MCAT. And there is actually an MCAT study guide in the front part of your book that will really help you out for those kinds of things. So that's just a little secret. The other part of this is don't overthink the problem. And you'll hear me, don't make the problem harder than it is. I'll say it over and over again. We'll also talk about palm to forehead moments. And believe me, I have palm to forehead moments too. And usually what happens is somebody's coming in and they show me their work on their problem and I follow along the merry path just like they did. And I come to the end and I go, well, I see how you got there, but I'm not sure where we took a wrong turn. So we will have palm to forehead moments. So the first thing is don't make this harder than it is. So the first question is asking, what is the total distance traveled? Well, we've got a car at a stop sign. So this tells us when we have a car at a stop sign, this is going to tell us some key information. This tells us that our initial velocity is equal to 0 meters per second. And we can start with our initial position as being 0 meters. And this is at time is equal to 0 seconds. So at a stop sign already communicates to us an awful lot of information. And we're going to travel a distance of 200 meters. So this is my final distance, or my X final of 200 meters. And the answer to this problem right here is 200 meters. I did not have to calculate anything in order to get the answer to that problem. But because it's in a physics book and it's part of the physics problems, most of you would go, okay, I've got to calculate something. No, don't make the problem any harder than it is. And we're given our total time. So our time total is 30 seconds. So we do want to draw a picture. So I'm going to draw my little car. And we've got a direction. If this is going to be a vector, because it's got direction and magnitude. We know that the total distance, so the second step is labeling the problem. So I know at t is equal to 0. We have initial velocity is equal to 0. And my position is equal to 0. At the final, I'm now at a position of x final is equal to 200 meters. We don't know the final velocity yet. And that's one of the things that we want to figure out. We also want to know at some point when we get to 100 meters, we want to know the time. So there's another problem that we're going to try and figure out. But we've got our distance, we don't know our final velocity. And if I'm looking at my equations of motion, there's something else we don't know. We don't know acceleration. And that's one of the things that we want to find out. So we can rearrange this a little bit. So we have our knowns. We have our unknowns. Our knowns are initial position and final position. We know our initial velocity. We know our initial time. Our unknowns are acceleration. We don't know that. We don't know our final velocity. And we don't know the distance at, oh, well, that's not what I want to write. We don't know the time at 100 meters. Those are the things that, those are our unknowns. Those are the things that we don't know. So you can go back and get the things that you know and you don't know. So I can do a change in position is equal to an initial velocity times time plus 1/2 my acceleration times squared. Oh, we do know our final time. Our final time is 30 seconds. This equation has variables x, t, and acceleration. We know x, we know t, we don't know acceleration, and that's one of the things we want to find. So this equation is going to help us out. So change in position is my final position minus my initial position. It's equal to my initial velocity times time plus 1/2 my acceleration times time squared. I need to rearrange to solve for acceleration. Well, first of all, let's get rid of the zeros. We know that that's 0. We know that that's 0. So we can simplify. So I get my final position is equal to 1/2 my acceleration times time squared. Just because it's been a little while since a lot of us have done algebra, I'm going to do it in gory detail. So I'm going to multiply both sides by 2. And I'm going to divide both sides by t squared. So now I have my final position, 2 times my final position times t squared is equal to acceleration. We know that the units of acceleration should be in meters per second squared. So let's make sure we've rearranged our equation correctly, and we're going to verify our units. So over here, I've got 2 times meters. I'm dividing by seconds squared. My units are meters per second squared. That's a unit of acceleration. That is meters per second squared. I have just verified that I rearranged my equation correctly. I've just verified that I've rearranged my equation correctly. So that's great. So let's solve for acceleration. So my acceleration is going to be 2 times, and we said my final distance was 200 meters. My time was 30 seconds. I thought I brought my calculator in. Okay, I got 2 times 200 divided by 30 squared. And then this gives me 0.44 meters per second squared. So now I've got my acceleration. So we now know what my acceleration is, and we can type that in, 0.44 meters per second squared. So we've solved for acceleration. Now we want to solve for the final velocity. Well, I've got my equations of motion again. So let's write our equations of motion down. So I've got x is equal to v initial times time plus 1/2 acceleration times time squared. I've got v final is equal to v initial plus acceleration times time. I got v final squared is equal to v initial squared plus 2 acceleration times my change in position. This is in variables of v, acceleration, and time. This one is in position, acceleration, and time. This one is in velocity, acceleration, and position. Now, which means that if I'm looking for the final velocity, that's what I'm looking for. I now know my final position is 200 meters. My time was 30 seconds. My acceleration, because we just figured it out, is 0.44 meters per second squared. I could use two of these. I could use this equation or I could use that equation because I know what my initial velocity is because we'll write that one down too. We know what my initial velocity is. So that just leaves me my final velocity is equal to my acceleration times time. We know velocity needs to be in meters per second. My acceleration is in meters per second squared times time, which is seconds. This gives me meters per second. So my units are all going to work out. That's a pretty straightforward way to do it. But I could have also used this one. It's not out of the realm of possibility. Both are correct, just that one's a little more straightforward than the other. So my velocity final is going to be my 0.44 meters per second squared times my time, which was 30 seconds. I end up in meters per second, so I've done those things right. And this ends up being like 13.3 meters per second. The next one we want to know is we want to know the time at 100 meters. We know the acceleration because we figured it out. We know the distance that we want to get. In this case, it's 100 meters. We know the initial velocity. So this case, we're probably gonna we're going, okay, I gotta figure this out here. I could look at this. This doesn't have time. Time's a variable I want to figure out. I don't know my velocity at 100 meters, so that one's not going to help me out. So I got to go back and use this first one again. So I'm going to do my change in position is equal to my initial velocity times time plus 1/2 my acceleration times time squared. That's 0. I want to solve for time. So now I'm going to have 2 times my change in position divided by my acceleration is equal to time squared. So let's look at my units. Time squared is going to be in seconds squared. So now I've got meters divided by meters per second squared, which my meters will cancel. And now I have 1/1/second squared, which is equal to seconds squared. So I've rearranged my equation correctly. So now I'm going to get 2 times 100 divided by 0.44. Gives me 454 seconds squared, but I'm going to have to get the square root. So time is the square root of that. And this gives me 21.3 seconds. So now we had our final velocities. We can come back over here and our final velocity was 13.3 meters per second. And the time required was 21.3 seconds. And we did our unit analysis all the way through. Questions?